So far, we have only one type of function that we can do the derivative of, and that's like basic polynomials. So the question is, well, what about other functions? How do we do the derivatives of sine and cos and e to the x and natural log of x, and what do they look like? So we're going to start with looking at our exponential and logarithmic functions. What do you think would be the derivative of e to the x? I mean, if you were following, I would think that if I learned what I've learned in this class up till now and I didn't know anything more, I would say, well, why not bring the x out in front and subtract 1 from the exponent? Because that's what we did with everything else. So that would be my guess. And it's not right. And you're going to find out that it's not right. But that seems like a logical kind of guess based on what we've done so far, right? So what I have for you guys is I've got this little applet that I made, and the black graph right there, I'll make it nice and big. No, that wasn't really nice and big, but let's move things right. There we go. That looks pretty. The black graph is the graph of e to the x, and the red line is a tangent. And the slope of this tangent line right now is 1. So there's a blue dot at 1. If I drag my tangent somewhere else, every time I drag it, it draws the slope at that point. And so it can make a graph. Here, I'll show you another one that you already know just so you can see how this applet works a little bit better. Let's open that one up. Let's just do a parabola. If you had x squared and I did all the tangents, what's the derivative of x squared? 2x. So when I drag this point along, it should draw a graph, and that graph should look like 2x. We'll see if that actually works. Does that look like, as it's graphing all the slopes, does it look like it's making the line y equals 2x? Yes. So this program, what it does is as you drag a point along there, it says, here, I'll move it up a little bit till it gets to a new point. Right. So at this point, at that point, 2.3, 5.27, I've got a derivative that's going to be 4.59, and it's graphing that point. And if it graphs all of those together, we can see that the derivative of a parabola is a straight line. If I changed my original function to x cubed, so let's clear everything here. That's not a cubed. That didn't work either. There we go. There's x cubed. Now it's off the... There's my point. If I graph this one now, what should I see as my derivative? A parabola, right? Let's see if that works. As I'm coming down, it's figuring out all those slopes, a little bit of a jump in there between. And that blue graph, of course, is y equals 3x squared. So now if we go to e to the x, what your job is I'm going to drag it along, and you have to look at the graph, recognize the graph, and tell me what its equation is. So that could be a little bit tricky, right? Because you can have all the transformations involved, everything possible. So if I drag it along here, you tell me what graph you think it is. It's the same thing. And this is the only derivative that does this. So if we go back to our notes here, the derivative of e to the x is e to the x. And that's partially why the number e is special. 2.71828, 1828, yes. Yes. So here I wrote it in Leibniz notation. You could also write it like that. So the derivative of e to the x is e to the x. And the fact that it doesn't change makes it easy and makes it confusing at the same time. So we're going to run into some problems later on because we're going to be confused that nothing changed. But yes, it stays the same. So e to the x is a really easy derivative to figure out. This next one is not going to be as easy for you, but I'm going to get you to try. Let's look at the natural log. So there is in black here we'll go like this. In black is the graph of our natural log. If I drag things along, whoa, close, closer, no. Yeah, okay. All right, I'll go to the computer. Smartboard orientation's off a little bit. Here we go. Let's grab this point. Oh, it's because I haven't clicked on that button. There we go. Now it should work. If I, yes. All right. What do we notice about the blue graph? Does the blue graph have, characteristics of the blue graph? Sorry? Looks kind of logarithmic as well, right? Now, a logarithmic graph does go up forever. Will this graph, the blue graph, go into the negatives? No. So there's going to be one little slight difference between our logarithmic graph and this graph. There will be an asymptote here at y equals 0, because since our log graph is increasing forever, the tangents will get flatter and flatter and flatter, but never equal 0. What about as we go, does our blue graph go into the negatives? If I kept going down. So there would also be an asymptote at x equals 0. It gets steeper and steeper and steeper and steeper, but it will never go into the negatives because we're never going to have a slope that's going in the negative direction. So now we have a blue graph, and I've told you there's an asymptote here and there's an asymptote there. What graph has those properties? A reciprocal graph. And the hard part to tell, and what you can't tell just by looking at it, is which reciprocal graph is it? It's just 1 over x. Of course, it's just the 1 over x graph when x is greater than 0, because the domain for natural log of x is greater than 0. So then the derivative would have that same domain. But when we write it and when we do our work with that, we're just going to say if we have natural log of x, the derivative is 1 over x. And for the IB calculus, this is the extent that we're going to do with our exponential functions and logarithmic functions. When you take calculus in university, or if you take the advanced math calculus course, they also look at 2 to the x and log base 3 of x, different bases. But for us, we're going to stick to e because it's the easiest. E is for easy. So now we have new derivative laws, and we can apply that and mix it together with the derivative laws we've already learned. So what did numbers in front do to derivatives before? just multiplied in front anyways. So the derivative of this one will be exactly the same as it was before. And we learned that if we add or subtracted functions, we could take the derivative of each of them separately. So derivative of the second one, well, the x cubed will be 3x squared. The natural log of x will be 1 over x, and it's multiplied by 3. So we get 3x squared plus 3 over x. And sometimes you're going to have to say, wait a minute, the x is in a place that I haven't done the derivative. So how can I manipulate things so that it is in a form that I can do the derivative? So you're going to need to look up your log laws again, get refreshed on them. What can I do with that 5x? I can move it out to the front. And what's the natural log of e? It's equal to 1. So this question is really f of x equals 5x. What's the derivative of 5x? Just 5. And we can do all of our tangent and normal ideas with these as well. So we want to find the equation of the tangent at the point 0, 1. Well, what do we need to do first? We need to find our derivative, which stays the same. Then we need to figure out what is our slope at that point. So when we plug in 0 for x, we get 1. That's the slope of our tangent. We can put that into our point slope form of our line. And here we would have our equation of our tangent. If we wanted the equation of our normal as well, then the slope would be -1. And here's just a graphical picture. The blue graph is e to the x. The red graph is our tangent. And the black graph is our normal.